In this video, we're going to study confidence intervals. Now, the motivation for this particular topic is that often we go out and we collect samples to learn something about our population, and often that thing we want to learn is in the form of our parameter. So if we're talking about categorical data, right, our parameter is going to be a proportion. So I want to be able to say something like the proportion of my population that has a particular attribute is this, right? And we want to be able to give that estimate of what that parameter is with some degree of confidence. Now let's take an example like a candidate running for office. So if that candidate's running for office, they might want to know, okay, what percent of people at this point plan on voting for me? So if they go out and collect a sample and count up, okay, out of this sample of so many potential voters, this percentage said yes, they'll vote for me. That's what's referred to as a point estimate. Now let's just kind of throw a number out there to have something to look at. So let's say they get a sample proportion of 0.42. So what that tells them is that in the sample, 42% of the respondents are going to or plan on voting for this particular candidate. Now, the candidate and us understand that it's very likely that 42% is not the actual number so the actual percentage of votes that the candidate is going to get. Not only that, but it's probably not even the exact proportion of potential voters who at this moment are going to vote for the candidate. Because when we take a sample, we know that there is just natural variation involved, right? There's just random variation that we wouldn't expect necessarily a single sample to hit the true number right on the mark. So because of that, while point estimates are nice, it would also be really nice to be able to ascribe some degree of confidence to not only the point estimate, but to a range of values that the true proportion is likely to be. And that's where confidence intervals come into play. So what we want to do is we want to take our point estimate, our sample proportion, and then we want to add and subtract some amount that we refer to as the margin of error. And in the end, what we want to be able to say is something like this in this example. We want to be able to say, something like, we are pretty sure between 39% and 45% of voters plan to vote for our candidate. So what this does is it takes into account the fact that we don't necessarily think that 42% is the number, but that point estimate also can lead me to being able to make a statement like this, that like, okay, we're pretty sure it's somewhere between 39 and 45%. And so in this particular instance, that would mean that we are taking the 0.42 as our point estimate, and we're adding and subtracting 0.03. So this 0.03 is what we refer to as our margin of error. So that's what we want to be able to do. But in order to do that, we need to think about what is an appropriate margin of error to subtract and to add to our point estimate. So to kind of develop that idea, we're going to look at an example here. It says, according to a Quinnipiac poll, 70% of 1,342 U.S. adults think that social media companies like Facebook and Twitter do more harm than good. All right, so you can see a sample has been taken, and we got a point estimate of 70% of 0.7. Now, we wouldn't necessarily assume that 70% is the true percentage of people that think social media companies do more harm than good. But it's also, we have no reason to think that it's way off either, right? It's a point estimate. We got it in a sample, so we think it might tell us something about the population. So what I want to do is get a sense for how much natural random variation we would expect when we take samples of 1,342 and ask them this question. All right, so we're going to go back to our simulator that we've used a lot to kind of try to get a sense for this. So in our case, we got 70% as a sample statistic, as a point estimate. So I'm going to put that in here. And what I want to do is simulate what it's like to have a sample of size, and what was our size again? 1,342. Okay. What's it like to sample with this size, assuming that it's about 70% in the population? What kind of variation do I expect in that scenario? So I'm going to click on proportion of successes. And what we're going to do is we're just going to collect a lot of these samples. We're going to simulate this over and over again. So I'm going to do this 1,000 times. Okay, and so we get this familiar curve here. You notice it's got kind of that normal curve shape to it. But what I'm interested in here is how much variation there is in these different sample proportions that we're seeing. And so I'm going to click on this, Summary Statistics. And what it tells me is that I have a standard deviation of 0.012. So standard deviation, remember, is what we've studied back in chapter 1 that tells us kind of how much variation from average we expect. So what we're saying here is that when you have samples of this size, this number 0.012 gives us an idea of the standard deviation, meaning how much variation do we expect from the average of 0.7, which is right in the center of the distribution. It gives us a sense of that. So whenever we're talking about the standard deviation of a sampling distribution, we give that a special name. We call it the standard error. Okay, but just understand that it is just simply the standard deviation, the same standard deviation we studied in chapter 1 of a sampling distribution. Okay, so we just found that we get a standard error of 0.012 in this scenario. So we've got our point estimate, we've got our standard error. Okay, now what do we do with this information? Well, now we use our knowledge of the normal distribution, right? We know that what's known as the central limit theorem, okay, it says that under the proper conditions, a sampling distribution is going to be normally distributed. It's going to be shaped like a bell curve. Okay, so we know that that's the case. That was what motivated us to study the standard normal curve in the first place. And the other thing I want you to remember is that in a normal distribution, 95% of the values fall within 2 standard deviations of the mean. So, in the case of a sampling distribution, the mean, or just the center of the sampling distribution, well, it should center on whatever the true proportion is, right? So if you're taking sample after sample after sample, then what we would expect is that if we went p plus 2 standard errors, right, which is just the standard deviation of this thing, or p minus 2 standard errors, that there is a 95% chance that our point estimate is going to be in this range. So what we'd say is that our point estimate has a 95% chance of being within 2 standard errors of the true proportion. But if that's true, I can also just kind of reorder the sentence to say that the true proportion P has a 95% chance of being within 2 standard errors of the sample proportion. All right, so that means that there's a 95% chance that the true proportion is between this number, 2 standard errors below the sample or statistic or the point estimate, or 2 standard errors above the point estimate. So between those 2 numbers. All right, so here it is, kind of all put together, right? So if that's the case, then what we can say is that we are 95% confident that the population proportion is in this interval, okay? And this margin of error that we've been talking about, we're going to define as 2 standard errors, because 2 standard errors goes along with this 95% number that we learned about for normal curves. All right, so we can apply this to our situation, right? So we have a sample proportion of 0.7 minus 2 times our standard error. And remember, we determined that the standard error was 0.012. And then the upper bound for my interval is 0.7 plus 2 of those standard errors. And so when I make that computation, 0.676 and then 0.724. So that is my 95% confidence interval for the proportion of the population that thinks social media companies do more harm than good. So what does this mean, right? What it means is that we are 95% confident based on our sample. We are 95% confident that between 67.6% and 72.4% of, and of course we're referring to our population here, okay? So of the entire population, so in this case, US adults, of US adults think social media companies like Facebook, and Twitter do more harm than good. So we introduced this idea of a confidence interval, and we said that we compute it by taking your point estimate minus 2 standard errors and take that up to your point estimate plus 2 standard errors. Okay, but this number 2, remember, was tied closely with the number 95%, right? And that came from the fact that we knew that on a normal distribution, we have 95% of our curve between a z-score of -2 and a z-score of +2. So on the next page here, we have just a slightly more generalized version. So instead of the number 2, you see this z star. And the idea is, if your confidence level changes, then the number you multiply the standard error by also changes. So this is the more general formula for our confidence intervals. And so just to get an idea of what the z star is all about, let's compute it for these 3 different confidence levels. So first of all, for 98%. So for each of these, I want to just sketch a quick normal curve. So for 98%, what I want to do is draw a picture so that between negative z and z, I have 98% of the curve. So what we want to do is determine, okay, if 98% of the curve is between negative z and z, then what's on the outside? Well, of course, there's 2% left, so half of it, 1% would be on the left, and half of it, 1% would be on the right, so that it all adds up to 1 or 100%. And then once I've determined that, we go back and we work with this same normal probability calculator again. And so I check my box here, and if I look, I can see to find this z star here, I want 0.01 to the right. So I'm going to switch this so it shades to the right. I'm going to type in 0.01 in for the probability, and it tells me 2.326. So in this instance, if on that example we just did, it had wanted me to be 98% confident instead of 95% confident, instead of multiplying by 2, I would have multiplied my standard error by 2.326. If we do the same thing for the 90% confidence interval, again, let's sketch a little picture. This time I'm going to leave a little bit more out on the edges, so negative z star up to z star should give us 90% right there in the middle. So that means we've got 10% left, so split between the bottom and the top should be 5% each. So 5% plus 90% plus 5% gives me a total of 100%. And so in my calculator now, my probability that I want to the right is 0.05. So 1.645 is what I get for a 90% confidence interval. And then finally for 90%, you might say, well, didn't we already determine that it was 2? And yes, we did, based on the 68, 95, 99, 7 rule. But I want to go ahead and go through the motions of calculating this using the method we just did. So between negative z star and z star, we want 95% here. So that means we have 5% left. So that 5%'s got to split between both the top and the bottom. So that leaves us with 0.025 on the left and 0.025 on the right as well. So in my normal probability calculator, we get 1.960. So the more accurate version of when you use a 95% confidence interval is to use 1.960 rather than 2. Okay, they're very close, of course. I would never mark you incorrect if you use 2 instead, but this is a little more accurate, so you might as well use 1.96. All right, so let's put all this into practice. So here we have the example that starts off with an article that's entitled "CSI Effect Has Juries Wanting More Evidence." And it examines how the popularity of crime scene investigation television shows is influencing jurors' expectations of what evidence should be produced at trial. So in a survey of 500 potential jurors, one study found that 350 were regular watchers of at least one crime scene forensics television series. And so suppose the study reported a standard error of 0.0205. So in A, it asks, assuming that it is reasonable to regard this sample of potential jurors as representative of all jurors in the United States, use this information to construct a 95% confidence interval for the proportion of all potential jurors who regularly watch at least one crime scene investigation series. And then this last part's important. It says, you may assume the necessary conditions are met so that it is valid to use the normal model. So remember earlier we said it's going to follow a normal curve. Our sampling distribution follows a normal curve so long as certain conditions are met. And we haven't talked tons about those conditions yet. We'll do more so later. For now, as you're just learning the mechanics of this confidence interval idea, just we can assume that they're met in this case. All right, so remember our formula for confidence intervals is this. Your point estimate plus or minus Z star times your standard error. So they gave us the standard error, right? Later on, we will figure out the standard error for ourselves, but not yet. So kind of for this first set of confidence interval problems, it's just going to be given to you. So we have that. Our point estimate, okay, well, that's our sample proportion, right? And they found that 350 in their sample out of 500 potential jurors regularly watch these shows. And so I guess their concern here is that maybe potential jurors are expecting too much evidence. I don't know, maybe that's what they're getting at. So there's our standard error, our sample proportion, and so we're almost there in terms of being able to apply this formula. We just need Z star. And we already figured it out just on our previous page, so let's just kind of piggyback off what we just did. But so that in your notes you're not kind of wondering, like, where did that come from again? Remember that we just did this from the previous example. So you just might make a note there. So to put that into practice, 0.7 plus or minus 1.96 times the standard error, which is 0.7 plus or minus 0.0402. And just as a little reminder here of the different vocabulary that we've been using, this 0.0402 is what we would refer to as our margin of error, right? That's literally the thing you're subtracting and adding from and to your point estimate. And then we actually want to do the addition and subtraction. So to actually subtract, you end up with 0.6598, and then to actually add 0.0402 to 0.7, you get 0.7402. So this is telling us, right, that we are 95% confident. And again, this is a conclusion about the population itself, right? So we are 95% confident that between 65.98% and 74.02% of potential jurors, it's always important to refer to the population we're interested in, So we're interested in potential jurors here, of potential jurors regularly watch at least one crime scene investigation series. Which is quite a bit, actually. Okay. Now in part B, what we want to do is the same thing, but we want a 99% confidence interval this time. Okay, so all the same information, same sample proportion and everything, but this time a 99% confidence interval. So sample proportion is still 0.7, standard error is still 0.0205, excuse me. But now we want to go ahead and sketch this out. And so we want to figure out what's happening so that the proportion of the curve between negative z and z is actually 99%. So if that's the case, then to the left, well, there's only 1% left over, so half of that has to be on the left, and the other half has to be on the right. So in my calculator, I'm typing in 0.005, which gives me 2.576. So that's my new Z star. Now, everything else remains the same for my computation, right? I'm going to take 0.7 plus or minus 2.576 times the standard error, which gives me 0.7 plus or minus 0.0528. So notice I'm adding and subtracting a bigger number than I did on the previous one. So this is going to give me a wider interval, 6472 up to 7528. Okay, now part C wants us to comment on this difference, right? So this one was wider, right, than this one, as you can see. Why is that? Well, we were more confident that the true proportion is in this interval. So if you want to increase your confidence that you capture the true proportion, then you better widen out your guess in order to be able to be more confident that you've captured the true proportion. So I might say it like this: we needed a larger interval in part B to be more certain we captured the true proportion. A good analogy that I like for this is to say, if you want to be more certain you catch a fish, then cast a wider net in order to be more certain that you actually catch a fish. All right, let's work through one more example here. I would really encourage you to pause the video and try this one on your own with the formulas that I've given you. All right, so it says from a random sample of 97 individuals, 13 were left-handed. Let's determine a 92% confidence interval for the proportion of the population that is left-handed. The study that this sample came from reported a standard error of 3.46%. State the meaning of your interval in context. And again, you may assume that all the conditions are met so that in fact a sampling distribution would be normal. So there's a couple little traps in this one that I wanted to just point out so that it doesn't bother you when you go to do homework and things like that. So first off, when it says the standard error is 3.46%, let's understand that in the previous problem, if I go back, and we talked about the standard error being 0.0205, understand that that meant 2.05%, right? It's just the decimal form of the percent. And it's the decimal form that we're using in this formula. So if they happen to report to you the standard error in percent form, make sure you go ahead and convert it back to decimal form before you try using it in your formula. Otherwise, you're going to get a very strange looking interval. Okay, my sample proportion, so that's 13 out of 97, so about 0.134. All right, then we need our z-star, and that's where we're going to sketch a normal curve. And this time I'm sketching it so that between negative z and z is 92% of the normal curve. But if 92% is in the middle, then that leaves us with 8%, so half of it, 0.04, has got to be down here, and half of it, 0.04, has got to be up here. So in my calculator, I'm typing in 0.04 and figuring out what that z-score is, and that's 1.751. So we've got the three numbers we need for our confidence interval at this point. So we've got 0.1340 plus or minus 1.751 times 0.0346. So that means that my margin of error here is 0.0606. Right, that's our margin of error. And so my confidence interval, and let me just be real clear so that there's no confusion at all about where all this is coming from. This lower one is literally me just taking 0.1340 minus 0.0606, and that gives me 0.0734. And in this one, I'm taking my point estimate plus 0.0606, and that gives me 0.1946. So all this to say, right, we sampled 97 people randomly. We found that 13 of them were left-handed, which means 13.4% of the sample was left-handed. And then because of my knowledge about how much variation I would expect when collecting samples like this, I'm able to, from that, give an interval estimate that I can be pretty confident in. So I am 92% confident. You could say 92% sure. I mean, you don't have to phrase it exactly like that, but we're 92% confident that between 7.3, sorry, I don't know what that number was, 7.34% and 19.46% of the population is left-handed. All right. One last example here, just to try to build our intuition for what's happening with these confidence intervals. This would be a good one to pause yourself and just ask yourself, in these situations, if everything else stays the same, would we expect our interval to narrow or widen. All right, so hopefully you paused and thought about that for each of these. So if I'm changing from a 99% confidence level to a 90%, I'm going from needing to be really sure that I captured the true proportion to not quite needing to be as sure. So what I would say is if I did that, then I would go to a narrower interval. And I would say it like this: if we are willing, right, if we are willing to be less confident, that we capture the true proportion, we can make a more precise estimate. So that's just kind of the intuitive reason for why it would actually be narrower. There's also a mathematical reason. When we're 99% confident, then our Z star, we found this earlier. We found it way back, sorry, where did we find that? Here we go, 99% confident. We found that the Z score was 2.576. When we're 90% confident, we found that Z was 1.64, sorry, way back here, 1.645. So in a 99% confidence interval, you'd be doing this. You'd be saying that plus or minus 2.576 standard errors. Whereas a 90% confidence interval, you're only adding and subtracting 1.645 standard errors. So that would be a way to kind of argue, yeah, mathematically, that's exactly what we would expect. This is a narrower interval than that one. But this is really the thing I want you to hang on to up here. This is almost more important to me. If you're willing to be less confident that you capture the true proportion, you can make a more precise, a more narrow estimate. If you were changing from a sample size of 80 to a sample size of 50, okay, well, if that happened, just think about in general, if someone said, I went and I asked 80 people this question, and another person went and asked 50 people that question, then you're going to have just slightly more trust in the larger sample if all other things were equal, right, in terms of the sampling techniques and everything, right? Because the more you sample, the less variation you expect from your sample results. So what we could say here would be that decreasing our sample size, decreasing the sample size means you will have more uncertainty in your sampling. Your sampling results. So what does that mean? This means your standard error will be larger. And if the standard error is larger, that's making your interval wider. All right, so hopefully these kind of questions here make sense. You'll be kind of asked similar types of questions in your homework to kind of really get you thinking about this idea of what is it that's controlling the width of our interval.